Okay, good day, guys. I'd like to start with an example that was given on the last lesson that was related to the rocket that is placed on the moon of Jupiter that's called as Ganymede, and it's rotating around it. As I mentioned before, the total energy of this rocket will consist of three energies. The first one is the potential energy between this universal gravitational potential, between this rocket and the moon that is called as Ganymede, and plus the potential energy between also this rocket and Jupiter, and the kinetic energy of these vibrations because it vibrates around the Jupiter with a certain speed. Let me write it as v1. And of course, since it's placed on this planet, it will have the same speed as v1. Let me write it here. And the velocity that we have to find is called as v escape. Now we have to find the escape velocity. And in order to do this, we have to calculate the total potential, total energy of this rocket that's placed on the moon. Now let's start with the potential energy that is between this rocket and the Ganymede. I'll of course write the minus sign times g and times mass of rocket and mass of Ganymede and over the radius of Ganymede that is already given. I see here the radius of Ganymede is 2.64. So I will place the numbers instead of letters. You see here that is minus 6.67 times 10 to the power of minus 11. I'd like to multiply by 1.495. That was the mass of Ganymede, and times the 10 to the power of 23. And over the radius, that is 2.64 times 10 to the power of 6 meters. So the number that will be appeared here, if you calculate it, will be 3.78 times 10 to the power of 6. Of course, I have here the mass here. I have to write it as mass. It's not meters. And the unit for the energy is joules. The mass of rocket is not given, but it will be simplified in the end. You'll see it. So I have to write it because the mass is present in the formula. The next one, the energy, potential energy between the rocket and Jupiter. I have to use the same formula, minus g times mass of rocket, but now I have the mass of Jupiter and the radius from Ganymede to Jupiter. So indeed, I have to calculate this distance here. It's already given as 1.071 times 10 to the power of 9. Indeed, I have to calculate the radius of Ganymede also, but it is, you see here, the distance or radius is 2.64 times 10 to the power of 6. The radius of this Ganymede. So you see here, it's 1,000 times smaller than the radius between the Jupiter and Ganymede, of course. So that's why it can be neglected. So I'll write it as radius of Jupiter from the Ganymede. So I put the numbers now, minus 6.67 times 10 to the power of minus 11 times the mass of Jupiter that's already given as 1.9 times 10 to the power of 27 kilograms. And over the distance that I said, it's 1.071 times 10 to the power of 9. So the energy here appears to be minus 11.83. Of course, I have the mass here of the rocket. Times 10 to the power of 7 times the mass and times joule. The unit of joule. But see here, the powers are different, so I have to. I'd like to write it in the same powers. So minus 118.3 times 10 to the power of 6 mass of rocket, and unit is joules. Now, in order to find out the kinetic energy, I have to find the speed here. In order to find the speed, I have to calculate the relation between the centripetal force that's applied to Ganymede and, of course, universal gravitational force that's attracting. So they are equal. The gravitational force equals to the force of centripetal. So the G times mass of Jupiter times mass of Ganymede and over the radius I write it as radius of Jupiter. It's not the radius of Jupiter, it's the distance between the Jupiter and the Ganymede. Square I have, and times mass of Ganymede times its V1 square speed and over the radius of Jupiter. I can simplify one of the radius here. I can simplify mass of Ganymede, and you see here that the V1 square will be equal V1, sorry, I'll write it as in the root, G times mass of Jupiter times radius of Jupiter, over the radius of Jupiter. So if I put the numbers, 6.67 times 10 to the power minus 11 times 1.9 times 10 to the power 27 and over 1.071 times 10 to the power 9, and I'll take all of this stuff in the root. So V1 will be equal to 183 times 10 to the power 6 in the root. So I'll have the speed of 1.09 times 10 to the power 3 meter per second. So that's the V1. Now I can calculate the kinetic energy, of course. The kinetic energy, of course, will be the kinetic energy of the rocket will be mv1 square over 2. So I'll write it in terms of m. If I put the numbers here, 1.09 times 10 to the power 3, I'll take it in a square times m, and over 2, I'll have the number of 0.59 times 10 to the power 6 m joules. Now the total energy, I'll have minus 3.78. I have to write the potential energy in terms of minus, you know that, 10 to the power 6 times m, mass of rocket, and plus, indeed, I have the minus here. That's the second one is also potential energy that is taken with the minus sign, minus 118.3 times 10 to the power 6 m, and plus, because I have the kinetic energy, 0.59 times 10 to the power 6 m. So the total energy appears to be, that is minus 121.49 times 10 to the power 6 m, and this energy should be equalized with the escape kinetic energy. Let me write escape kinetic energy with the total energy, but now I won't use the minus sign because I deal only with the numbers now. So my kinetic energy is m times v escape square over 2 will be equal to this number, 121.49 times 10 to the power 6 m. So you see here the masses are simplified now. So my escape speed square will be equal to 249 98 times 10 to the power 6. And if I take the root of this, I'll have the number that is 15.6 times 10 to the power 3 meter per second, or that's the same as 15,600 kilometers per second. So that's the escape speed that you have to give to this rocket to completely escape from this planet and go to, infinity, somewhere here. So escape from the gravity of Ganymede and from gravity of Jupiter. So you have to give this velocity to a given rocket. Now we continue with the new topic. I'd like to name it first of all. That is called as Kepler's laws. So that's one of the fundamental fundamental laws of a planetary motion. The first and important impact for the astronomy science was given by Claudius Ptolemy, that is drawn in the first picture. Claudius Ptolemy, a Greek astronomer in the 2nd century. So his idea was that every planet, I mean, the moon and the other stars are rotating around the Earth. So his theory or his model is called as geocentric model. So I mean that the Earth is in the center, and moon and other stars are rotating around it. So that's the Earth, and that's the moon. So he said that he predicted that every planet and every star is moving around the Earth. So this model called as geocentric model, Claudius Ptolemy. So his model was one of the first model that was predicted by human being, and that was valid. That was used for 1,400 years after him. After him, Danish astronomer, Polish astronomer, in 1543, Polish astronomer, he was from Poland, Nicholas Copernicus, predicted that all the planets are vibrating around the sun. We have the sun here, and other planets are vibrating around it, around the circular orbit. So this model is called as heliocentric model. That was the first model after 1,400 years after Ptolemy's theory. Nicholas Copernicus said that all the planets are vibrating around the sun, around the circular orbits. So this model is called heliocentric. And after that, but he just predicted this model. He said that all orbits are circular orbits and they are rotating around the sun, but he didn't calculate any calculations. He just predicted this. And after him, Danish astronomer Tycho Brahe just measured and make some measurements and calculations about 777 stars that was visible by naked eye. He just measured and make some observations on the stars, and he collected some data related to this, related to the movement and periods of these vibrations. He just collected some data about the periods, and about the orbits. But his data were not enough to make some formulas. So his student, German astronomer Johannes Kepler used his collected data of his teacher and make some calculations for about 16 years. And he just find out the orbits are not exactly circular. He said that the orbits are elliptical, ellipse, not circle. So his calculations was very, precise when he calculated and make the formula related to the vibrations of Mars around the sun. Because the ellipse that was drawn by Mars around the sun was very precise and very close to ellipse, because as the distance that were covered by the Mars around the sun was so ideal. So his calculations was very We're very precise related to this. Now, before we come up to these calculations, we have to understand what's the ellipse first of all. So this geometric figure that's drawn here is called the ellipse, and the farthest end here, or farthest dimension, that is 2a, is called as measure axis. So that's why the A side here, that is drawn from the center of this ellipse, from the center of the orbit of the ellipse to its edge, is called as semi-measure axis. And the shortest dimension here, that is indeed 2b, that's 2b, is called as minor axis. So that's why B is called as you understand, semi-minor axis. And the points here that are shown, F1 and F2, are called as focal points. And the distance from the center to these focal points is denoted by C, and it's called as focal distance. So what's the relation between A, B, and C? That's so simple. That's A square, the square of semi-major axis equals to the sum of semi-minor axis and plus the focal distance square. So that's the formula for the ellipse. And Johannes Kepler predicted some laws that will be described in 3 laws, collected in 3 laws. So here are these. First of all planets move in elliptical orbits with the Sun at one of focal points. So he predicted that we have 2 focal points here, and the planets are vibrating around it with a certain speed. And one of the focus of this, the Sun is placed. So Sun is at one of these 2 focal points. The second one, radius vector drawn from the Sun to a planet sweeps out equal areas in equal time intervals. What does it mean? It means that if I have, for example, my planet moves from this point to here in the time of interval of t1, and the shaded area that was covered by the planet in this time interval equals, if I have the same time interval here, of course the speed will be different here, and here it's v2. And if I have the same time, delta t2, the area that was swept by the radius vector, that is shaded area, this one, between these 2 points, will be equal to this one. So let me write here, if delta t1 equals delta t2, it means that area 1 will be equal to area 2. We will come up to the mathematical calculations for this one, and we'll see it. And the third one we'll also calculate it. We will see the scientific method of this. The square of the orbital period of many planets is proportional to the cube of the semi-major axis of the elliptical orbit. What does it mean? It means that the third law, that was the second one, and the third one tells us if I have the time required to complete the circle, the ellipse here, it means that the square of period to a cube, that is a semi-major axis, is constant for all the planets that are vibrating around the Sun. That's called the third law of Kepler. Now we'll see the mathematical description for this. We'll try to derive the formulas, and that will be more clear, I think. Now, suppose that, first of all, since we have the closest maybe satellite, the closest point for us, or the closest star for us, is the Moon, that is vibrating. Our Moon, is vibrating around us. So some calculations were made by Newton, and he said that the Moon has got its own centripetal acceleration, and the mass, the object, now we have the apple here, legendary apple, that's placed on the surface of the planet has got its own centripetal acceleration, and there should be the relation between these two. Now, what will it be? Let's see. Now, let's start with the apple here, because that's on the surface, my first case. I'll write the centripetal force exerting to the apple, m times v squared. We'll suppose that it is moving with the speed, the center speed, let it be v1, v1, will be equal to the universal gravitational force. Of course, I have here the gravitational force and I have the centripetal force. They are in balance, so that's why I write it. Now, first thing that I've written here is centripetal force of centripetal. I wrote it here. Here. And now I'll write the universal gravitational force, that is G times m, mass of apple and mass of Earth, over the radius of Earth square. Now I can simplify the masses of apple, and you see here, if I simplify, so v squared over r here, this expression will give me the centripetal acceleration, or this is, I call it as gravity. So the gravity here equals g times mass of Earth over radius of Earth square. Now let's talk about the centripetal acceleration of Moon in the second case. I can write that by simple logic. Mass of Moon times its acceleration, it's denoted by here A of m. AM equals g times mass of Moon times mass of Earth, and times the radius, the distance from Moon to the center of Earth square here. Again, I can simplify the mass of Moon. So my centripetal acceleration will be equal to g times m of E over rm squared. So if I divide both sides here, both equations, what I'll have? I will divide the second one by first, so mass of centripetal acceleration of Moon over the gravity. So I will divide this equation by this one. So first of all, I divide the left side and the right side, of course. So g of mass of Earth over rm squared. I have to turn upside down the second one. So re squared over g times me, mass of Earth. I will simplify this. So you'll see here that the radius of Earth square over radius of from Moon to the Earth square is equal to 8m times g. What does it mean? It means that I can find centripetal acceleration I can keep the centripetal acceleration, so that will be equal. I know that, by the way, the radius between the Moon and the Earth is 60r. So I can write that AM over G will be equal to radius of Earth square over 60r square. So it is 3,600 radius of Earth square. I can simplify the squares here. So my AM will be equal to gravity over 3,600. So that is, if I calculate G as 9.8 over 3,600, I will have the number 2.72 times 10 to the power 3 meter per second square. So that's the centripetal acceleration of the Moon. On the other hand, I can also prove it by another method, that is v squared, the speed here, the speed of the Moon vibrations over radius from Moon to Earth. If I know the period, I know that the speed here will be equal to 2pr of moon over t. So I can write here that it's 2pr of moon over t squared and over radius of moon. So I can write here that is 4p squared times one of the r is simplified, so I have here 60r and radius of earth, sorry, and over the period. I know the period is about 27 and 32.32 days, or that is 2.36 times 10 to the power of 6 seconds squared here. So the number will be exactly as 2.72 times 10 to the power of 3 meter per second squared. So these calculations were made by Newton, because universal gravitational force was calculated by Newton and gravity also. So you see here, there are some relations between the attraction and universal force, and of course the radius squares here. If we have the radius squares for the acceleration and their ratio, we can find out the gravity, of course. Now, if we come up to another point that we'll try to prove the third law, so Kepler's law. Let me write here that is third law. That's made by Kepler. We'll suppose that we have the object, the planet is vibrating with the speed here, that indeed in physics we call it as linear speed, and it has got its own radius. Now, as we mentioned before, there are two forces that will be in balance. The first force is centripetal force, and the second force is universal gravitational force. So let me write here that the universal gravitational force will be equal to the centripetal force. So universal gravitational force is capital G, times mass of sun and times mass of planet over the distance squared, over r squared. And the centripetal force is mass of planet times its speed squared over the distance, that is r. Now, how can I find the speed? I can find the speed in terms of period again. I know that speed in a circular vibration is equal to 2pr over t. So if I plug this expression instead of v here, the things will be changed a bit. So my g times mass of sun times mass of planet over r squared will be equal to mass of planet times 2pr over t, or period squared, and here in denominator I have the r again. So g times mass of sun, I simplify the mass of planet, over r squared will be equal 4p squared times r squared over r times t squared. So one of the r is simplified. So I'll have here the t squared will be equal 4p over g, capital G, universal gravitational constant, and mass of sun, and multiplied by r cubed. So you see here, I can write this, the things that are in brackets are all constant, because universal gravitational constant is constant, mass of sun is constant, it's not changing, and p also is constant, it's 3.14. So let me name this constant as k sub s, constant of planetary motion, or Kepler's constant, let it be 4p squared over g times m of sun. So that has a certain value, that is 2.97 times 10 to the power of 19. If you look at the units, it's second square over meter cube. So I can write here that is t squared over r cube equals to the constant volume. So that was the third law of Kepler. So the ratio of squares of period of planets that are vibrating around the sun to ratio of semi-major axes of the r cube equal to the constant number. That was the third law of Kepler. Sorry. Now, calculate the mass of Sun using the fact, let's solve one example, using the fact that the period of the Earth around the Sun is 3.156 10 to the power 7 seconds, and its distance from the Sun is 1.496 times 10 to the power of 11 meters. Now, what should we do? We know that T squared over R cubed equals 4 pi squared. We've derived this formula just before over mass of Sun. So the mass of Sun will be equal 4 pi squared times R cubed and over G, universal gravitation constant, and T squared. So I will plug the numbers. That is 4 times 3.14 squared times the radius that's already given. That's 1.496 times 10 to the power of 11 cubed, and over the G, that's 6.67 times 10 to the power of minus 11, and times the period, that is 3.156 times 10 to the power of 7 squared. We'll have the number that is 1.99 times 10 to the power of 30 kilograms. So that will be the mass of Sun that you can easily calculate. Here are some data used for planetary data, and you see here that there are some masses of the planets are already given. So the radius vectors and periods, mean distance from the Sun, that is the semi-major axis A, and that's the period, and the ratio of T squared to A cubed, you see here they're approximately the same. So you see here that's 2.97 10 to the power of minus 11. See? Okay, so that was the data. Then I want you to copy this table into your exercise book also. And now we'll try to understand the second law that was derived by Kepler. Second law. Now, first of all, I'd like to say that the torque that we passed in ninth grade is equal to force times distance. Our force is gravitational force, and the distance is r. But since they are parallel, the torque is equal to 0. So I mean that the gravitational force times r equals to 0, and that equals the torque. On the other hand, the torque equals delta L over delta T, whereas the delta L, indeed the L, is the, we've covered this when we passed the Bohr's radius and the Bohr's postulates, and we said that L is angular momentum. So the angular momentum delta L over delta T is also 0. When it's 0, it means that delta L is 0. When the delta L is 0, it means that L is constant. So I mean that m times v times r is constant for all planets. So what does it mean? It means that if I try to calculate the area that is covered by the planet that is vibrating, so the area of this rectangle equals dr. What's this r? Dr is this side times r. But since I have dA here, that is shaded area, dA, when I calculate dr over dr times d, and that's exactly half of this. So I have to divide it by 2. And I know that dr here is equal to v times dt. So that's why v times dt times r over 2. Or let me write in more convenient way, vr times dt over 2. And I know that vr here, you see here, vr, instead of vr, I can write VR equals L over M. So I mean M over planet, I'm right. So dA over dt equals L M over 2 mass of planet. That will be constant. It means that in equal time intervals, if the dA equals dt, I mean if dA to dt is the ratio of these two is constant, it means that delta A over delta T, for whether it be delta A for delta T, and this is delta A2 equals to delta T2, and they are constant. So it means that in the same time intervals, if I have here delta T1 and it sweeps areas of A1, let it be A1, and here if I have the same time delta T2, and it will sweep the same area A2. If this delta T1 equals delta T2, it means that A1 will be equal to A2. So that's the mathematical description and conclusion for the Kepler's law. It's not a basic consumption. It can be proved also. Now, let's solve one more example. Let me give it for you. This example can be solved also by you. You will try to do it. Let me give you a hint that the L1 will be equal to L2, and you try to do it your own. Okay, let me read it. A satellite of mass of m moves in a vertical orbit around the Earth. The minimum distance of satellite from the Earth is called as perigee, indicated by P. And you see here that is the nearest point here. And if it has a speed on that point, and the maximum distance is called apogee, and that is the farthest distance. If the speeds of the satellites at point P is Vp at the nearest point, and the farthest point is Va, what's the speed at point Va? You have to find it in terms of Va. How many A will it be? I mean Va in terms of Vp. It will be half of Vp maybe, okay, or 1.5 of Vp, maybe root of 2 Vp, I don't know, and you have to calculate in terms of Vp, I mean, okay. So I just make a joke here, and you have to find it your own by using the law of the angular momentum, the conservation of angular momentum that was derived by Kepler. And the last thing, the Kepler's laws are not valid only for planets. That can be also valid for any celestial bodies that are moving around the sun. And the picture that you see here is called as Halley Comet. Halley Comet. And it rotates around the sun. At one of the focus we have the sun, and this Halley, and this comet, I mean, let's be a comet, Halley Comet, is vibrating around the sun, I mean, and it can be seen only when it's close to the sun, because it takes some light from it, and it happens only in 76 years. So I mean, once in the 76 years, it means that the period of the Halley Comet is approximately close to the 76 years. So that was the interesting fact that I want to share with you. So let's make a summary. So first of all, we started with this problem solving, and we said that there are some, we stopped on a history. So we stopped on a history first of all, history. So there are some names that I wanted to know. That is Ptolemy. Ptolemy, his geocentric model was famous for approximately 14th century, geocentric model. What he said that all planets and stars are vibrating around the Earth, and the center of these vibrations is Earth. And the second brief calculation was made by Nicholas Copernicus. His prediction was very brave. He said that no, all planets are vibrating around the sun, and he just developed his theory, this heliocentric model. He said that all planets are vibrating around the sun, around the circular orbits, but later Tycho Brahe collected some data, but he didn't make any predictions. He just collected some data. He just measured the movement and periods of 777 stars that were visible by naked eye. But his student, Johannes Kepler, used all his data and make some laws. There were three laws. The first was that all planets are moving around the elliptical orbits at one of the focus of which the sun is placed. The second law tells us that the area swept out in the same time the intervals are equal. If delta T1 equals to delta T2, then the areas will be the same. And the third law that was derived by Johannes Kepler, that the ratio of period squares to the cube of semi-major axes is constant. That is 2.97, approximately 10 to the power minus 19 seconds squared to meter cube. It was constant for all planets, not only planets. We also mentioned that it is constant for the comets and all celestial bodies still rotating around the sun and which are in the solar system. Thank you very much. Let's call it today. I hope that you will solve the problem and send me again.